In this video by the Aggie Math Learning Center, we'll be covering how to solve systems of equations. We will work through 3 problems that use different approaches to solve these types of problems. In our first problem, we are given 2 equations of lines, 4x plus y equals 16 and 2x plus 3y equals 18, and are asked to find the intersection of the 2 equations. Pause and take a moment to give the problem a try. The goal of this problem is to find a coordinate pair that is the point in which the 2 lines cross. There are multiple approaches to solving this problem, but I'll walk you through one called substitution. We do this by solving one of the equations for either x or y, and then substitute the solved form into the other equation. This simplifies to an equation that only has one unknown, which we can then solve for. For example, we can take the first equation, 4x plus y equals 16, and solve for y by subtracting 4x from both sides to get y equals negative 4x plus 16. We can then plug in negative 4x plus 16 for each y in the second equation, leaving us with 2x plus 3 times negative 4x plus 16 equals 18. Next, we distribute the 3, which leaves us with 2x minus 12x plus 48 equals 18. After that, we combine the x's to get negative 10x plus 48 equals 18. We then subtract 48 from both sides, leaving us with negative 10x equals negative 30. Once we do that, we divide both sides by negative 10 to give us x equals 3. This is the x-coordinate of the solution, but we also need to know what the y-coordinate is. We do this by plugging the x value we found into any of the equations we've used, and solve for y. I like using the one we've already solved for y because I won't need to solve for y again. Once we plug our x value into the equation solved for y, we will have y equals negative 4 times 3 plus 16. We then multiply the negative 4 and 3, which leaves us with y equals negative 12 plus 16. Simplifying the right side of the equation tells us that y equals 4. Therefore, the final solution is the point 3, 4. For our second example, let's look at the equations 8x plus 3y equals 34 and 32x minus 6y equals 28. We are asked to find the point of intersection of the 2 equations. Pause and take a moment to give the problem a try. For this example, we'll solve the system of equations using a method called elimination. In this method, we want to add or subtract the equations together to eliminate one of the variables, which leaves us with an equation that has only one variable to solve for. Looking at these 2 equations, there are 3 y's in the first equation and negative 6 y's in the second. Remember that the goal is to cancel out a variable by adding or subtracting the equations together. When I see negative 6y, I think, okay, this is just 2 times 3y and is negative. If we can multiply 3y by 2 and add that to negative 6y, we will get 0. Because of this, I like to multiply both sides of the equation by 2 so that we can get 6y, and then add the 2 equations together by adding the 2 left sides together and the 2 right sides together. Now, after thinking that through, let's work it out and see what we get. We start with the first equation. When we multiply both sides of the first equation by 2, we get 16x plus 6y equals 68. We can then add the 2 equations together. This will give us the following: 16x plus 6y plus 32x minus 6y equals 68 plus 28. You might be asking why we can add 2 equations together. Algebraic properties allows us to add whatever we want to one side of the equation, just as long as we add the same thing or something equivalent to the other side. Since we know 16x plus 6y is equivalent to 68, we know we can add 16x plus 6y to the left side of the second equation and its equivalent value 68 to the right side. From here, we can simplify this by combining like terms to get 48x equals 96. If we have multiplied the first equation by the right value, there should only be one variable left. The equation only has x's, so we know we chose the right multiplier. We then divide both sides by 48 to get x equals 2. Now that we know what the x-coordinate of this intersection is, we can plug it into either of the original equations and solve for the corresponding y-coordinate. Let's use the first equation. When we plug in the x value, we have 8 times 2 plus 3y equals 34. This can be simplified to 16 plus 3y equals 34. Then we can solve for y by subtracting 16 from both sides to get 3y equals 18. And then divide by 3 to get y equals 6. Now we know both the x and y coordinates that satisfy this system of equations. Therefore our answer is the point, 2, 6. We've now used two different methods to solve systems of equations. Notice that the goal of both methods is the same. Remove one variable so that we can solve for the other one, and then plug the value in to solve for the other variable. Both methods can be used for either problem. It is just a matter of preference on which one you'd like to use. As a general rule of thumb, you usually will use substitution when an equation is already solved for one of the variables, or pretty easy to solve for that variable. The elimination method is generally used when the equations are formatted similarly so that we can get variables to eliminate when adding or subtracting the equations together. But ultimately, either process is valid to use. For our final problem, let's consider these two equations, x squared plus y squared equals 16, and x squared plus y squared plus y equals 19. We are asked to find the points of intersection of these two equations. Pause and take a moment to give the problem a try. We will use the method of substitution for this problem, but then again, elimination is also valid. Because the first equation says that x squared plus y squared is equal to 16, and we notice that the same thing is found on the left side of the second equation, we will replace the x squared plus y squared in the second equation with 16. This will give us 16 plus y equals 19. You can then solve for y by subtracting 16 from both sides to get y equals 3. Now that we have solved for a y-coordinate, we can plug that into one of our equations in order to solve for our x values. I would use the first equation since it is a little simpler. When we plug in 3 for y, we will get x squared plus 3 squared equals 16, which will simplify to x squared plus 9 equals 16. After subtracting 9 from both sides, we get x squared equals 7. Therefore, both the square root of 7 and the negative square root of 7 are x-coordinates that correspond to our y-coordinate of 3. Because there are two x-coordinates, we will have two solutions. Our solution set is therefore root 7 and 3, and negative root 7 and 3. Finally, in all of these problems, it is a good idea to check your work. You can do this by plugging in the x and y coordinates into both equations and making sure that both equations are satisfied. If these or any other concepts require some more of your attention, feel free to watch this video again, reach out to your professor or recitation leader, or utilize the free tutoring services offered at the Aggie Math Learning Center. We hope this video has been helpful.